Okay, so if I'm not mistaken, today is our last lecture, at least according to kind of official scheduler, that it's 15 weeks of lectures, then final exam on week 16 for kind of graduate level courses. And today is week 15, if I'm not mistaken. Okay, and as I promised, so our main goal today is, okay, let me change my usual agenda. So today our main goal is to kind of prove total mirror relation. And kind of let me start with reminding what is the main theorem, and then we will split proof of the main theorem into 3 steps, and the first 2 steps will be review of what happens last time. So there will be last time, but slightly later. Okay, so main theorem works in the following way. So we have X, which is toric variety. And it is given in terms of a polytope. And the polytope itself, Ex, is essentially kind of intersection of these half spaces labeled by collection of integer vectors. Say A run from 1 to, I think we call it capital B, EA. So that is our toric variety. Essentially, it's compactification of some space Rn by collection of hyperplanes. So these are our hyperplanes, HB1, HB2, and kind of our polytopes is essentially intersection of positive half spaces constructed from this hyperplane. In this case, we have 4 hyperplanes, which are lines in 2 dimensions, and they intersect over this space, which is what we usually call radial part of X. So that is our data about toric variety. It is essentially, so toric variety equal to this data, we call it Dx, which is collection of these primitive integer vectors, which are normal vectors to these hyperplanes. So that is our combinatorial data. And we also will use capital M, the complex dimension of this X. Okay, so on this toric variety X, so we compute tropical Gromov-Witten invariants. So we compute them on X. And in our case, we will look in case of G0, tropical Gromov-Witten invariants, and kind of arbitrary degree beta. And here, as labels, we have some collection of cycles, gamma 1 to gamma n. So gamma alpha, they are some representatives for some cohomology classes. And this tropical Gromov-Witten invariant, it only depends on cohomology classes for this gamma alpha. And then we do the following thing. So we weight this expression with kind of some formal parameter q to the power beta. So this expression is kind of q1 to beta 1 and so on. Beta m, where m is second rating number of x. So we perform the summation over all these betas. So that is kind of our A side. So A side is some well-defined enumerative invariant in the form of tropical Gromov-Witten invariant. So there is kind of a separate conjecture, which is proven in some cases, so the conjecture theorem, which is tropical correspondence. Which essentially is formulated in very easy way that we can omit kind of word tropical. So therefore, if you kind of afraid of thinking of tropical Gromov-Fit invariance on left hand side, kind of in the most cases that we discuss, like some projective spaces or products of projective spaces. So this tropical correspondence conjecture is actually a theorem. The tropical Gromov-Fit invariance exactly equal to ordinary Gromov-Fit invariance over complex numbers. So that is our kind of expression on A side. So that is our A side. And expression on the B side has the following structure. So we have a collection of polymorphic functions, phi gamma 1 to phi gamma n. And here we compute correlation function in Landau-Ginzburg-Saito model with a superpotential double. Right. So that is kind of main statement of the theorem. So theorem basically a statement that there is an equality. So let me mention. So phi gamma alpha are sort of mirror dual gamma alpha. So they belong to polymorphic functions on some space which is C star to the power capital N, which is the same as complex dimension of X. So these brackets is LGS correlation function. And it is WX is known as a mirror superpotential. And it is constructed in terms of this combinatorial data. Covered in blue. We have this combinatorial data in blue, and it's constructed in the following way. So we take summation. I think we call them A from 1 to capital B. And here we have QA e to the I y paired with A. And then it's our mirror superpotential. So mirror relation works in the following way, that on the left-hand side, we have toric variety X given in terms of this combinatorial data. We have some generating parameters, Q1 to Qn, Qm. And we have some collection of observables, which are just some representatives of cosmology classes on X. So using this data, we can construct some polynomial with integer coefficients, like polynomial in these Qs, and these guys are integer because they are answers to some enumerative problems on how many curves passing through this and this cycle. So this thing is essentially kind of polynomial in Q with integer coefficients. And to be more careful, because it is counting problem, so it is actually non-negative integer coefficients. So coefficients say the zero or positive number, and these positive numbers they have some enumerative interpretation. And the right-hand side, which is correlation function in Landau-Ginzburg-Saito model. So this kind of cosmology classes gamma mapped to some observables phi gamma. And let me be even more precise. So this phi gamma alpha they would be essentially defined in terms of good section Wx, let's say of classes gamma alpha. So earlier we discussed that the kind of cohomology classes of toric variety X, cohomology ring of toric variety X, isomorphic to kind of Jacobi ring by mirror superpotential, which is this O of P star capital N quotient by gradient ideal constructed from this Wx. And this isomorphism means that there is a identification between kind of cohomology classes here and classes, equivalence classes in this Jacobi ring. So we need some identification, and to construct these holomorphic functions, so what we need to do, we need to apply good section, which is a map from Jacobi ring to holomorphic functions. So it's kind of chooses special representatives for these classes in Jacobi. So we take cohomology class here, map it to class in Jacobi ring, apply good section, get holomorphic function, substitute it into correlation function for Landau-Ginzburg-Saito model, and then kind of surprising fact, which is kind of not entirely obvious from definition of this thing, that the right side is also kind of polynomial in Q, and even less obvious that coefficients are actually positive in Q. So that is kind of some surprising fact, and unfortunately I don't have time to get into details how it works. Okay, so that is our main theorem, and kind of the proof of the main theorem will require us to kind of derive mirror superpotential. So we essentially want to derive a data in Landau-Ginzburg-Saito model starting from a data in kind of tropical Gromov-Fit invariants. So let me work here. So kind of idea of the proof, or not idea, strategy. The proof, so we start with the left-hand side. So kind of first step is to take tropical Gromov-Fit invariants, and then we cast it in terms of HTQM amplitudes. So then the step 2 is do some resummation of HTQM amplitudes. So this HTQM amplitudes is some kind of additional auxiliary object that we introduce to kind of manipulate with this kind of left-hand side and turn it into right-hand side. And then step 3 is kind of localization to Landau-Ginzburg-Saito model. So that is kind of schematic strategy of a proof. So three main steps. So tropical Gromov-Fit theory into HTQM amplitudes. Then some resummation of HTQM amplitudes, like from one type of amplitudes to other type of amplitudes, and then kind of final step is localization to Landau-Ginzburg-Saito model. Now finally we reached kind of a reminder from last time. So apparently last time we discussed these two bits. So last time we proved kind of theorem that works in the following way, that this very same tropical Gromov-Fit invariant of degree beta, okay, on X with some insertion gamma 1 to gamma n, okay, weighted with u to the power beta, summed over beta. So this very same object actually equals to some linear combination of amplitudes, which we defined as correlation function. So that was correlation function of n states that correspond to this observables psi gamma, or this observables gamma. So this psi gamma states, they will essentially have this very simple form, so differential for gamma and then 0 for the vector. And then here we have kind of generalized states associated to compact-defined hyperplanes, and here have the following formula. So we have arbitrary number of these insertions, and here summation from n from 0 to infinity. So that was kind of our first theorem that we proved last time, and this Wx is kind of has a structure that starts reminding this mirror superpotential. So that's the reason why we choose this notation. But it was defined as this formal linear combination. So once again, with the same number of generated parameters QA, all these states psi b. So they are some states that are associated to this compact-defined hyperplanes, and they have the following form. So it is 1 in kind of in a place of differential form, and vector b in a place of integer vector. So that was essentially this what we call theorem 1, which is relation expressing like re-expressing tropical Gromov-Fit invariance in terms of HGKM amplitudes. So this kind of brackets. So they were essentially summation over some amplitudes. Like if here we have an observable, so it is summation over all trees with n leaves, and there is some amplitude, and it is weighted with the size of automorphism group of this tree. So that was okay, essentially combination of these amplitudes. Okay, so that was one theorem that we proved last time, but we also did some kind of resummation of these amplitudes, and the pictorial picture was the following. So when we look at this correlation function, which is sum of amplitudes, it is essentially summation over some trees. We kind of draw these trees in white, and then on these trees. So these trees have like a number of white leaves, equal to n, and then kind of number of red leaves equal to n. So and due to some property that the amplitude on the red subtree vanishes, so we can interpret the summation over all these graphs with n plus m leaves, with n leaves decorated by these psi gamma observables, and red leaves decorated by W. Okay, so we can kind of rewrite it as a sum over this white trees with n leaves decorated by arbitrary number of red leaves in kind of arbitrary place. So that was kind of one of the observations, that we can simplify this correlation function to this formula, and then we say it. There is a theorem, we call it theorem 2, which was essentially a statement like this. So let me kind of write down the very same sum, which is 1 over n factorial, and from 0 to infinity, so this psi gamma 1 psi gamma n, wx, n times. And this was computed in kind of A-type HTKM. And in this A-type HTKM, we have vector space Q, G plus minus mu and G. So we kind of reform this A-type HTKM into family of HTKMs that we use different color. It's white. So and the deformation is only happens through deformation of supercharge. Okay, let me use this notation. And all these guys remain the same. So parent, multiplication, G plus minus, and the vector space remain the same, but we deform our differential Q. And the statement is that this amplitude, which is A type HTKM amplitude, that it equals to a different type of an amplitude where we have psi gamma 1 this upper script x, psi gamma n upper script x, and here we have q wx, and that's what we call B type HTKM. And kind of the key difference is that previously we have the summation and insertion of compactifying of this data from compactifying hyperplanes, and now we kind of completely sort of absorbed this summation and this data about w of x into deformation of this states psi gamma and deformation of our differential cube, or deformation of our HTKM into family parameterized by W. So for psi gamma, so this psi gamma, so psi gamma x, I think we propose the mirror states. And the construction was the following. So it starts with psi gamma, and then we do the following thing. So we take kind of our propagator, like kg minus, that we insert on internal edges, and apply it to psi gamma, multiply it by the universal state. And we kind of iterate this procedure. So the next one will be kg minus, and here will be wx. Okay, so here like multiplication the two. So kg minus multiplication wx. And here we have kg minus multiplication wx by gamma and plus dot dot dot. So essentially we are addressing this state psi gamma by kg minus multiplication on wx. So that is kind of our mirror state, and it has this graphical interpretation. So previously we draw it as kind of a solid or fat yellow lines, and the pictorial picture was like this: that this fat yellow leaf is kind of ordinary white leaf. And then we dress this white leaf by kind of arbitrary number of red leaves, remembering that on each internal edge we have kg minus, here psi gamma, and here is another. And then we just repeat this dressing kind of multiple times. So it's psi gamma. And now we have two wx insertions, and it creates two internal edges, so it's 2 kg minus applications, and so on. So that is kind of a formal way to realize this arbitrary dressing by red lines by saying that that we take a formal sum of all external leaves, like undressed, dressed by one red line, say dressed by two red lines, and dressed by arbitrary number of red lines. And the similar picture is for Q, and let me write it here. So Q WX was a Q plus the following thing. So that was G minus commutator with multiplication by WX. So the formula for Q only has like one deformation term, so that is different from psi gamma. Like psi gamma has this infinite sum, while Q has only one term. However, the kind of deformed propagator, like A associated to this Q, which is essentially something like 1 over Q, will be 1 over Q plus something. And expanding this thing into formal geometric series will give us a kind of similar sum for fat yellow internal edges, and kind of each term, the term with n G minus insertions would be a term where we dress this internal edge by n red lines. So that was essentially a statement of theorem 2 that we started with a particular collection of amplitudes, which we resummed into these nice object correlation functions, and then we observed that due to some properties of various states in these amplitudes, we can rewrite the sum over correlation functions with arbitrary number of WX insertions into a single correlation function where we kind of turn these arbitrary red insertions into deformation of states and deformations of our HQM.
Is it the order of insertion WX then to KG minus? It's like KG minus must be on the left.
Yeah. Sorry, you got correct. Yes. My bad. Yes. Yes. So KG minus should be on internal edges. Yeah, and then this one. Okay. Thank you. Okay. So that was kind of quick recap of what we did last time. And kind of last time we essentially did. I'm not sure. Like judging from kind of formal number of steps, we did like 2/3 of a job. But the third step is kind of harder. So essentially, first 2 steps was our first paper, which was like 80 pages, and just doing the third step was another 80 pages paper. So even though kind of as a logical steps, we have like only half as many steps as in the first 2 steps, but this one is kind of technically and structurally is more complicated. And just another remark for Louis, who might be watching this, that essentially like steps 1 and 2 were done in kind of Lossev and Frenkel in 2-dimensional setting, while step 3 kind of wasn't done. So the best formula that they got is kind of relation between kind of tropical between Gromov-Fit invariance and some kind of amplitudes in B model HTQM with a mirror superpotential. While in a tropical case, we can do one step further to get all the way to Landau-Ginzburg side. Okay, that was side remark, and now. Okay, so I still want to keep main theorem, so I think I will just erase this part, especially theorem 1, because we are kind of not going to return to tropical. Okay, a bit too much. Okay, let me restore the state, because I will need that. So let me restore the states, and that is some from one vector x to a psi B, and psi B A is 1 4. Okay, so today, so to kind of achieve a step 3, the first step that we will do, we will kind of rewrite or reformulate A type A. Yeah. So we need to reformulate it to kind of adapt it to this kind of deformation. And as I proceed, you will see why we. So the key kind of point in reformulation is actually changing our kind of changing the basis in our vector space. So our original vector space was kind of invariant differential forms u1 to the power capital N, invariant differential forms on the historic variety X, tensor with n-dimensional edges. So the states here were differential form and some integer vector. So now let us do several reformulations. So first of all, let us recall that if I have differential forms on X, so let us for a moment forget about invariance. I can say that differential forms on X as a space isomorphic to kind of functions on the following supermanifold X. So it is kind of tangent bundle to X with a parity shifted by 1. And this identification works in the following way. So here differential form is some kind of collection of functions I1 to Ik, and here we multiply by kind of basis in one form. So to get function on cotangent space, so here kind of PTX is sort of fiber over X, and on X we have a coordinate little x, and here psi is a coordinate in a fiber. And kind of a way to get from a differential form a function on PTX. So let me call this function f subscript omega to indicate that it is a function kind of associated to this omega. And okay, let me even call this map capital F. So capital F omega is the following. So we take this collection of components, and now we replace psi dx's by psi's. Psi 1, psi ik. So this thing is kind of function on PTX because on functions on PTX because psi are odd variables. So all functions of odd variables are essentially some finite polynomials in psi, and we interpret these coefficients for homogeneous polynomial of degree k as the components of differential form. So the kind of the non-trivial part in this simplification, you need to check that that these things transform correctly under kind of coordinate transformations of X. That on the differential forms like this one forms dx, they will transform as a derivative of some transformation. So essentially they will transform by Jacobian. And here these psi's which are fibers on PTX would also transform by multiplication by Jacobian because of this kind of vibration structure Okay, let me. That's one. Okay, so that is kind of one step that here, instead of thinking about differential forms, we will think about functions. And once again, so here invariance means that so this U1 invariance means that the action, the Lie derivative with respect to kind of arbitrary vector field from, let's say, vector field from this U1 action acting on differential form is 0. And similarly here, we can reformulate the C derivative as a certain vector field acting on this function and preserve. So there is a notion of kind of invariant functions. Okay, so that is kind of one reformulation, and this reformulation is kind of rather technical. Okay, rather convenient reformulation. So that would make a certain kind of operators looking more natural. While in principle we can use somewhat more complicated and maybe a bit more confusing notations, but still work with differential forms. So this one is kind of sake of convenience, while reformulation 2 is kind of an important conceptual reformulation, and it is essentially a Fourier transform. And at least when we discuss mirror symmetry in physics literature, so I think kind of community believes that mirror symmetry is some kind of refinement and reformulation of a T-duality, and kind of the essence of T-duality is a Fourier transform somewhere. So T-duality essentially goes from kind of windings to modes and goes from kind of periodic delta functions to periodic exponents. So that's why, at least in all cases that I know, like the construction and the proof of mirror symmetry, at some point it contains a certain Fourier transform. And in our case, the Fourier transform is done with respect to this integer variables m. So we treat with e to the n labels as labels for Fourier series. Okay, I need to write something. Essentially, what we say that now we will replace kind of these z labels by the following structure. So we say that now our states they are kind of these functions for etx cross some s1 to the power capital N. So the elements here will be some function that is function of three types of variables. So there is variables x from this pkx. There are variables psi that are responsible for that are representing this basis in differential form. And then there will be variables capital Y that will be variables from S1. And once again, we can expand a function of this y, of this periodic variable y. So kind of almost y variables yk, they are identified up to 2 pi integer shift. So any periodic function, so we can expand it in Fourier series. So that will be, and because we have multiple variables y, so here this Fourier series will be labeled by integer vector in n-dimensional lattice. So for each variable y, we have its own kind of integer number labeling Fourier harmonics with respect to this one. So that will be, once again, the Fourier harmonics will depend on x and psi. And here will be e to the n variables y. So therefore, like any function here is essentially a collection of Fourier harmonics, and we want to identify this function fn with kind of state that is differential form that is the function and integer vector n. So therefore, essentially, we are kind of choosing a different basis, and this different basis is just some infinite linear combination of previous basis vectors, which were in the form differential form and little n, and now we take a summation over all n's and weight it with e to the my. So that is kind of two reformulations that we do to our A-type HGM. So here we did nothing fancy. We just kind of relabeled vectors in our infinite dimensional vector space. So we relabeled them in a different way. So we say that instead of working with a paired differential form in integer vector, let us work with a paired differential form that is function of some periodic variables y. Okay, so what about kind of our other data, q, g plus minus? So we kind of reformulated y. Let me put it y check. So that should just rethink it. So and we have multiplication and a pairing. So let us see how these objects reformulated in terms of in a new basis. So okay, let's start with the q. So q was originally de Rham differential in this basis. So de Rham differential acting on differential form in this basis. So it did nothing to this label n, and in kind of new basis. So this thing works in the following way. So we have psi k d over dxk. So essentially, when we act on these components, so all we do, we kind of increase number of psi's, and number of psi's associated with the degree of differential form. So we increase degree of differential form by 1, and we also take a derivatives of this component. And that is essentially what de Rham differential does. And we do this thing, this qx diagonally on these Fourier components. So it kind of doesn't mix components with different m. So component with a fixed m go to component with the same vector m. Okay, so now g plus minus. So okay. So here I need to before formula g plus minus. I need to specify a little bit. So because x were coordinates in a toric variety, so on a toric variety we have kind of decomposition into radial and angular coordinates. So this differential is de Rham differential in all coordinates. So it has this structure. Okay, let's call it capital K, capital N. And here it's capital N because we have like twice as many x variables as r's and y's. So that will be what? So for dr, we say that it is psi radial, and for d phi, we will denote it as psi angular. So it is psi angular k, d over d phi k, plus psi radial L p over d r L. And then, because we are working on invariant differential forms, so invariant differential forms, as we said before, they don't have this any dependence on these angular variables. So therefore, essentially, this form kind of acts trivially on invariant differential forms. So trivial on kind of invariant u1 to the n invariant differential form. So essentially, our de Rham differential is kind of a radial de Rham differential, so it acts non-trivially only on kind of radial dependence of our differential form. Okay, so now G plus minus. So for G plus, previously it was substitution of a vector field into differential form, and this vector field, it kind of was defined using these components of vector M. So now in this new reformulation, so what we want to do, we want to get some kind of differential operator, and this differential operator should decrease number of psi phi, because substitution of a vector field, it kind of eats up 1 degree of differential form. And then this vector field should depend on M, but unfortunately after we kind of turned M into y's, so the only way to get M back is to take a derivative with respect to y. So therefore, G plus is a differential operator where we differentiate with respect to yk and differentiate with respect to psi k phi. So and you can check that action on this kind of linear combination is the same as a substitution of kind of this angular vector field with components equal to vector A. And sorry, G minus, and then for G plus, we are changing just one thing, so we are changing derivative with respect to angular phi to derivative with respect to radial phi. So in kind of this notation for Q, G plus, and G minus, so it became immediately obvious that they all square to 0, because here we have a kind of derivative, either multiplication by odd variable or derivative with respect to odd variable. And these things typically square to 0. So in this new reformulation, a certain properties of say G plus and G minus became manifest. And similarly, Hamiltonian in this formulation like U and G plus will be some differential operator that will contain some derivatives in kind of R, Y, psi, psi. But that thing is kind of not very interesting. Yeah, let me read that part of here. So I still want to kind of keep this state. I want to write them in new basis. Okay, so what else do we have? So we have Q, G plus minus. So now multiplication. So previously for multiplication, we took like a form with integer vector, another form, integer vector m2, and then the result was the following. So we take a wedge product of the forms, and we add this vector. So now in this new basis, so multiplication on kind of pair of functions f1 and f2 is just pointwise multiplication of functions. So
excuse me, in G plus, why it is dy? Okay.
because original G plus, it should substitute radial vector field whose components in a standard basis equal to vector m. And so action of G plus was the following. So vector m was preserved. While here we substitute radial vector field, like we call it m d over dr, into omega. So now we need to get m. So how do we get m from function of y? We differentiate with respect to y. And differentiation with respect to y doesn't mix the exponents. So it kind of preserves the exponent but returns exponent multiplied by m. And then we just contract this m with d over d psi r, and that essentially produces what we want, that we do not mix exponents, and kind of we only perform some action on coefficient, and this operational coefficient depends on kind of on integer vector and exponent. So the same works for multiplication, that now we have this kind of linear combination of coefficients and exponents, and if we multiply these two sums, so what we would get? We would get like product in y variables, product of two exponents will be exponent with the sum of integer vectors. And then this exponent will be multiplied by exactly product of their coefficients, which is product of differential form. So we see that in this new basis, the multiplication, which kind of was still relatively kind of straightforward, but still it was some kind of twist on top of ordinary wedge multiplication, because we need to do something with that. But in this new basis, it is a very standard operation. It's just multiplications on functions on some supermanifold, which is ptx times s1 to the power n. So now, and the similar thing with a pairing. Like previously for a pairing, we also need to kind of do two things. So we need to check that m1 plus m2 were added up to 0. And then if they add up to 0, we take a wedge product of differential forms and integrate it over x. So now G on pair of functions f1 and f2 is very simple. So we take a product of f1 times f2, and then on this supermanifold we have some standard integration measure, and we integrate over ptx and s1 to the power n. So integration over s1 to the power n will pick up a Fourier mode with kind of zero integer vector, because that's the only function that integrates non-zero over this n-dimensional torus. And that is essentially like S1 integral here ensures that we impose this condition. While integral over ptx is kind of with the standard Bayesian on a ptx, it is the same as integral of the corresponding differential form. So therefore, kind of using these notations, we get kind of a lot of simplifications, and the last but not least simplification is the following. So because now mu is kind of ordinary multiplication, and the RAM differential is just ordinary first order differential operator, so the Leibniz rule is kind of follows automatically. It's just a Leibniz rule for differential operator acting on functions. So we don't even need to kind of check what happens to n's. And furthermore, we have this very complicated 7-term relations that were relations between multiplication and G minus. And now the 7-term relation is nothing but a property of second order differential operator. So and verification of it is rather straightforward. So when we apply differential operator to product of say two functions, so then we would have different kind of terms. It's either differential operator acting on one of the functions, or we have some kind of cross term which is something like a bracket. When one derivative acting on the first function and second derivative acting on the second function. And then kind of by taking a smart linear combinations, we can actually eliminate this bracket part. So and that is the origin of 7-term relation. That is kind of analog of Leibniz relation, but for a second order differential operator. Okay, so what about our states? I kind of kept them for quite some time. Okay, so state psi gamma is differential form gamma and 0 here. So the corresponding function will be just y-independent function. So that will be like function of x and psi. So these states psi gamma, they also have very natural interpretation as y-independent functions. So it's y-independent. And now it is clear why G plus and G minus act trivially on this state, because G plus and G minus involve differentiation with respect to y. Okay, so what about this other states psi b? So for psi b, the story is kind of more complicated. So this state fb. So this thing is just a pure Fourier harmonic. So we just take a Fourier harmonic with this integer vector b. So or essentially, if we take a linear combination, so this wx is a function of y only. So therefore we have like two types of states in our HTQM. So states that are y independent, that only depend on x and psi, that correspond to our kind of cycles or our observables in a Gromov-Itten theory. And we have different kind of states which are purely functions of y, just some periodic functions of y which are independent on x and psi. And these functions, they kind of responsible for this combinatorial data for x, for this compactifying hyperplane. Okay, and now it's kind of became more and more clear that in these new notations, like this wx, which we introduced as a formal object, like a formal linear combination of particular type of states in original basis in A type. So now in this new basis, they start looking like functions of some periodic variable y, and if we treat this periodic variable y, not even remark, it's kind of prediction, observation. So observation, so we can treat S1 to the power n as embedded as kind of angular part of C star to the power n. And this C star to the power n, so that is essentially our mirror dual to toric variety. And these functions w of x, which are only functions of y variables, so we can treat them as kind of holomorphic functions in this C star to the power n. So holomorphic functions, they are essentially like functions of half of the variables. So we kind of select like half of the variables in some space, and then just say that our object depend only on this half of the variable. So here we treat S1 to the power n as kind of half of this space. so as an angular part. And then the function of y variables, we can treat it as a holomorphic function on c star to the power n. So here there could be some subtleties with this kind of analytic continuation and stuff that I kind of do not plan to discuss in our course. So for now we just make this observation that we start getting some y variables, and these are familiar y variables in kind of this Landau-Ginzburg-Saito model, where we work with holomorphic functions quotient by gradient ideal for some mirror superpotential. So we see that this thing and the structure for this W of x, which was some formal combination of these compact defined states. So after we performed this change of basis, it looks kind of identical to mirror superpotential. And that is kind of a first signature that we are on the right track. That because in order to get this kind of red expression, we need kind of two ingredients. We need kind of mirror superpotential, and we need some collection of holomorphic functions for this observable count. So far, getting mirror superpotential turns out to be very easy. That we changed this, we performed this Fourier transform, exchanged m variables, m kind of variables on n-dimensional integral lattice. We replace them by these new y variables on n-dimensional torus, and in this state that we use to kind of decorate our amplitudes, so that are our kind of red insertions. So suddenly it became some linear combination of exponents, and this linear combination of exponents surprisingly just kind of identical to mirror superpotential. So if we formally by this procedure compute W of x for a given toric variety and compare it with the final answer, so they would be identical. But once again, here is just a kind of a thing on the level of observation, that we got some function that actually in some intermediate step, because here we are still inside of HTQM construction. So we still haven't seen any kind of residue formulas involving this W of x. So that was some intermediate step in HTQM rewriting of amplitudes. But surprisingly, this step kind of gives us a very strong hint that we are getting towards the mirror. And that was kind of essentially main result of Lossev and Frenkel, that they got this mirror superpotential, and then they say that we can use it in Landau-Ginzburg model with this mirror superpotential to kind of reproduce Gromov-Witten value. However, we only did like a first half step in part 3, because we actually didn't do anything. We just reformulated A-type HQM in a different basis, and we observed that certain kind of objects or certain arguments of some correlation function that we use to express tropical Gromov-Witten invariance, that it suddenly has a form identical to our expected answer for mirror superpotential. So what we're going to do after the break, so we are going to kind of see like how to actually kind of turn this W of x into kind of actual mirror superpotential, and how to get this kind of residue formulas for W of x, and how to get this phi. So I think right now it's 11:01. So let's make 11:01. Let's make 8-minute break. 11:09.
Let me ask. And here, can you remind how can we go from the homology to Jacobi ring? Because now we have the recipe to have the super potential Wx. But why this Jacobi ring will appear?
So that was kind of part of a standard mirror construction. So I think we kind of never proved it in general, but we kind of proved it in some simple cases like CPN. For CPN, we just observed that here homology ring is just some kind of p of x over x to power n plus 1. Okay. So here I need you are right. It's not cohomology ring. It's quantum cohomology ring. So for quantum cohomology ring, you need to subtract q, and we verified like for CP1 and CP2 that with a mirror superpotential constructed from compactifying dividers, we actually get this very same ring for quantum cohomology.
Okay, so this isomorphism is due to some standard results for toric variety.
Yeah. So that is actually a standard result for toric variety. So people like working in toric geometry, they kind of say that it's rather trivial part.
Yeah, but now we have an A model for this gamma of alpha. We can translate gamma alpha into this gamma 0 state.
Yeah, so far we haven't seen this part in quantum mechanics, and that's kind of what localization stands for. That so far we are dealing with some kind of deformation of this H-type HTQM. So we will write explicit deformation, but now we are dealing all our kind of states and operations. They are happening in this big superspace PTX cross S1 to the power n. While here in Landau-Ginzburg-Saito model, we kind of expect that everything happens on just functions of y. So, and that what localization stands for is kind of a way to remove this R and psi dependence, to say that that in these correlation functions we can choose a different representatives, which is kind of not a general function, but something like a function of y only. And then we will see that say 3-point function in these new variables will look very much like.
But you mean this f gamma, which is y independent part, also can be translated to something like
So f gamma, So this f b and w of x. They are kind of objects that have interpretation on the right hand side. While this states psi gamma, so psi gamma itself, it has like worst y dependence possible. It is y independent, and when we will kind of turn them into mirror states, when we will dress them with kg minus multiplication by w of x, we will get some complicated function that will be function of all variables, because this kg minus multiplication between this object and this object would kind of take a product of something y independent and something psi x independent. So that would be as complicated as it can get, and we want to kind of turn these complicated objects into just some holomorphic functions of y. And that will require some insights here. Okay, let's take 5-minute break. noise. Okay. Yeah, let us describe deformations, B model, B type, HTTP in this new basis. Okay, let's start with deformation of Q. So just to avoid carry this double subscripts like Q, W, Z, and W, Q, W, X. I will just call it QX, like Q plus G minus commutator with multiplication by WX. So that was our kind of expression for this one parameter family of deformations, or family of deformations parameterized by discrete data of toric variety X. So let us write down it as differential operator on these functions of functions on PTX cross S1 to the power n. So this thing is very easy. We say it, we are working on, we are acting on invariant functions. So this Q part is just a radial Durand part. Okay, and here G minus was essentially derivative with respect to y and derivative with respect to psi phi. So when we commute the second order differential operator with kind of multiplication by holomorphic function, so what we will get essentially first order differential operator that works as follows way. So we take the derivative of this Wx by yk, and here we have a first order differential operator which is derivative with respect to xik. Okay, so some factors of I that I somewhere. Okay, I'm working up to some numerical factors. Up to numerical factors, structurally, this kind of family of HTPMs is kind of original Durand differential plus this additional kind of a new differential in psi phi variables and kind of coefficients of in the basis of derivatives in psi phi. They are kind of partial derivatives of some function Wx with respect to yk. Okay, so and kind of this Q squares to 0 for obvious reasons, because when I square to 0, there are no cross terms, because here is psi r, here is d over d psi phi, here is derivative over r, and here is function of y. So there is no cross term, and in this term, so observe that Qx is actually sum of two differentials. So we call it Q, and for this differential, let me see whether we can name somewhere. Okay, let me use the name from our paper. So this one is kind of radial Durand differential and some differential QW that kind of essentially second part. Yeah, and that is QW.
Yeah, actually, using the V check HTQ-DQM model, which means the Fourier transformation of the previous V.
So
we have a Q, but not this one. We have a Q which is dr plus d phi. Right.
Why dr plus d phi?
Previously,
we are working on invariant forms. We are still continue working on invariant forms. So So that's why our Q doesn't have any psi-phi d over d phi part.
Excuse me, in the last class, you write
Yes.
Q equals to this.
Yeah, but then I crossed this first term because we are working on U1 invariant forms. So U1 invariant forms means that our functions. So what we say is that we are working on functions on tx cross s1 to the power n. But we also want to work on kind of U1 to the power m invariancy, and this thing essentially means that that here our functions are functions on kind of radial coordinate. That elements here they have like dependence on radial coordinate, dependence on psi r, psi phi, and dependence on y. So there is no dependence on little phi. So x is kind of roughly Rn and s1 to the power n with radial coordinate here and phi coordinate here. And invariance, U1 invariance implies that any differential operator like d over d phi acting on this function x by 0. So that is this condition that Lie derivative in kind of previous picture acting on differential form was 0. So essentially this U1 invariance means that there is no phi dependence. Although we still keep d phi dependence through this psi phi. And therefore action of kind of the full de Rham operator on this space of functions is equivalent to kind of action only of the radial part. And that is the reason why we kind of have this Qx as a sum of two differentials. So it's radial de Rham differential and some other differential operator acting on d over d psi. Okay, so let us. Okay, we will return to this in a moment. So what I want to do? Okay, so before we will return to kind of a general construction. Let us kind of study an example when x is just v1. So in this example, kind of qx is very simple because we only have one psi r, one psi phi variable, one r variable. So that is just psi r d over dr plus dw over dy. E over d psi. Okay, but kind of the more interesting part is to get a very explicit formula for a mirror state psi gamma x. So on a P1 we have only kind of two non-trivial cohomology classes. So it is kind of top forms and the constants. So therefore let us compute this thing in two cases. So let us compute it for constant, for identity, and for a top form, which we can treat as concurrent globe at some point. So here, let me write something here. So gamma 1 is just 1. So just a constant form. Okay, representative from this H0 plus just constant differential form equal to 1. And representative from a top cohomology class or two forms. So we will choose it as U1 invariant or U1 average at delta function on a point. So that will be R minus R naught, dr, dphi. So, and we observed that this thing is essentially a limit, tropical limit of Fubini's 2D form. So that is kind of very natural observation. And what we want to construct kind of mirror states for both of this thing. So for a constant form, mirror state is rather easy. So we take psi gamma which is just the very same constant. It doesn't contain any dr d phi's. So there will be no psi r psi phi's. And then the part which is kg minus applied to a product of psi of wx and psi1. So here, because the product is just ordinary product on functions, so I will stop writing mu, because as we say, mu is just ordinary. So here what happens? So psi1 is kind of just a constant. So when we say psi1 is just 1, and kind of g minus, as we said before, it contains derivatives with respect to y and with respect to psi phi. So there is a y dependence, so w of x, but there is no psi phi dependence. So this thing just vanishes, and kind of mirror dual to a constant form is again a constant form. And probably you wouldn't be surprised that kind of h naught here would map to sort of constant elements from this Jacobi ring. So for constants, nothing interesting happens, but for one forms, thing became interesting. Use a different word. So let us recall formal definition. So we take this psi gamma e, and we start tracing it with kg minus. Okay. Yeah. So P1 is a compactification of a line by two hyperplanes in the form of 2 points. So that's why the mirror superpotential is essentially q plus e to the iy. Okay. Sorry, I'm not very careful with this I signs, but sometimes they will appear, sometimes they will disappear, right? I apologize for that. Let me kind of remove them everywhere, because I'm not careful with them. So essentially we have two kind of inward pointing normal vectors, which is +1 and -1. So therefore we have exactly two exponents in our mirror superpotential, and we introduce this formal parameter w plus and w minus, and that is mirror superpotential for P1. Okay, so what about psi gamma p? So we say that we want to write down this state that corresponds to the state gamma p comma 0 in this new basis, and in the new basis. So what we essentially need to do, we need to replace dr and d phi by psi r and psi k. So that is kind of our A model state that correspond to this kind of tropical observable that is delta function on the point averaged over U1-ish. Okay, so let's start computing it. So this will 1 over delta r minus r minus psi r psi phi. So that is the first term here. And now we need to apply G minus to this product of WP1 psi gamma p. Okay, so yeah, I should give more space. Okay, so let us first put 1 over 2 pi in front, because it kind of commutes through all these differential operators. So now let us recall that this homotopy k was e to the minus dh g plus g minus dt integral, and g plus g minus applied to this very same product. Okay, so this product WP1 psi gamma, it was 1 over 2 pi, the delta function r minus r naught, psi r, psi phi, and then multiplied by the sum of two exponents, q plus e to the plus a by q minus e to the minus a. Now g plus g minus, they take derivative with respect to, so g minus derivative with respect to psi phi, and derivative with respect to y. And similarly goes with g plus. So therefore, what we would get the following formula e to the minus ph. And then here, taking this derivative with respect to psi phi and psi r, each one, so they will completely strip this psi r, psi phi dependence. So what we will get the following formula is delta function of r minus r naught. And here, by taking two derivatives on e to the y, it still gives us q plus e to the y. And similarly here, yes, each derivative would give us minus sign, but two derivatives would give us the plus sign back. So now what we need to do, we need to apply e to the minus th to this expression. Okay. I still want to keep this corner inside. So let me okay, let me continue in this part. Okay, now we need to apply e to the minus th, and we can recall what our and that here h is our kind of original Hamiltonian in A model. So the Hamiltonian A model, what kind of Lie derivative in this radial vector field, like m d of dr. And I think we talked like few lectures ago how the exponent of minus Lie derivative act on some differential form. So that is essentially like acting on differential form understood as a function of kind of r and the r phi variables, or psi r, psi phi. So the action is the following. So we just kind of shift this coordinates along the vector field for a time t. And for a constant vector field, the formula was like r minus mt, and psi r, psi phi stay as they are. So therefore here, so what we need to do. So here the story is a bit more complicated because this h would kind of contain d over dy derivative. So the vector field would be determined by these exponents. So therefore here we would get two terms. So there will be a term when we act on this q plus term. So nothing happens to e to the y because all y derivatives preserve e to the y. While in the delta function r minus r naught, we would shift with m equal plus 1. So we would shift our radial dependence by minus t. And similarly for q minus, e to the minus y, but here instead we would shift our radial position in kind of, we will shift by minus 1 times t, so that will be plus t bar. Okay, and now we can evaluate this integral. So let us write that we will have two types of terms, q plus over 2 pi e to the y, and let us evaluate this integral. So in this integral t goes from 0 to infinity. So t is always positive, and kind of delta function has support only when its argument vanishes. So and outside of this point it is 0. So therefore the integral is 0 if we never hit kind of 0 argument of a delta function, and 1 if we hit this argument. So what is the condition for hitting this argument? It means that t should be equal to r minus r naught. But because t is positive, so the only way to hit the delta function if r minus r naught itself is positive. So therefore the answer to this integral is Heaviside theta function of r minus r naught. So it is 1 if r minus r naught positive and 0 otherwise. So similarly, so the second integral we can analyze in a very similar way, because here we have plus t and t is positive, so the integral is only non-vanishing when this very same difference is negative. So here we kind of carefully evaluated this term. So this term for kind of this delta form observable will give us this kind of function. And once again here you see that in the first term we don't have any y dependence, but now in this second term we have some mixture of y and r dependence. Okay, so what about next term? So what about next term? What about this term? So for this term, what we need to do, we already computed yellow part. So yellow part is this kg minus wx gamma b. And then to compute this orange term, what we need to do, we need to multiply yellow part by wx and apply kg minus. But as we saw, kg minus, it kind of removes one copy of psi r and one copy of psi phi because of kind of g plus in k. But in this expression, we already have 0 psi r and psi phi. So therefore, this orange term is just 0. And that is kind of general property that if we have toric variety x, then any observable in toric variety is a differential form of some finite degree. So it contains like some finite number of psi r and psi phi. And then this kind of application of kg minus, each application of kg minus strips one pair of psi r and psi phi. And therefore at some point we will strip all psi r and psi phi's, and this infinite kind of series, they will always terminate. So therefore, even though in our construction, for this mirror states, we have this formal infinite sum, but this infinite sum always terminates, and it is actually a finite sum. And furthermore, this finite sum will be a polynomial in these variables q plus and q minus. So each time we kind of multiply by w of x, we will multiply by this formal variable. So So therefore, this thing will be some finite polynomial in this variables q plus and q minus. And we want to track this q plus q minus dependence because we know that left-hand side, which is tropical Gromov-Witten invariant, they are some finite polynomials in this q variable. So that's the reason why we want to keep track of it. Okay, so we have this kind of formula, which is very explicit formula for a mirror state for a P1 for this delta function at the point observable. So it contains this observable itself plus some function of R and Y. So let me erase this technical computation and let us kind of look at this answer. So here, so observe that phi dx has a parameter R0. So R0 was the support of our delta function. So that was choice of a point on a real line. However, this kind of different values of R0 is nothing but different representatives of the same cohomology classes. So different R0s different representatives from same cohomology class. And this cohomology class is just kind of H2 of P1. So we just kind of moving point and moving point is kind of adding a boundary of something. Okay, so therefore kind of, and we know that the left-hand side, which is tropical Gromov-Witten invariance, it is defined on classes. So that's why the answer should be independent on R0. So let us try to kind of take a limit. So therefore, let us take a limit R0 goes to plus infinity. So when R0 goes to plus infinity, we see the following thing. So this theta function of R minus R0 because R0 itself goes to plus infinity. So for argument of this theta function to be positive, we need R to be larger than R0. So, and if R0 goes to infinity, so essentially this theta function never achieves any value outside of 0. So similarly with this delta function, so delta function has support at R0. So if we are taking this limit pointwise, so look at this thing pointwise, so then we will never encounter this delta function. So delta function of R minus R0 is essentially also 0 everywhere on say finite R. While the last term, so the last theta function, which is R0 minus R0. So once again, for any finite R, we are smaller than R0 that goes to plus infinity. So therefore, this thing is essentially everywhere 1. So the pointwise limit. So let me put parentheses because it's kind of pointwise limit. So pointwise limit means that if you take like anything with a finite support, multiply, integrate, then essentially we will get the same as kind of contracting it with the value of the limit. So here we will get just the following formula: q minus e to the minus 1. So we observe an interesting fact that yes, we have this very complicated mirror state that depends on all four variables, on r, psi phi, and y, but it has a parameter. And if we take this parameter to infinity, then we can get rid of r and psi phi dependence and get only function of y. And that is what we kind of desire as a result of this localization, is somehow turn this mirror states into some functions of y. So, and that what we would like to call phi gamma p. But you can immediately notice that the problem is somewhat symmetric. So if you take r naught going to minus infinity instead of plus infinity, we will get a different function of y. So if you take the same thing, r naught goes to minus infinity, so we will get another function which will be q plus over 2 pi e to the y. So that would be phi gamma p tilde. So now there is kind of natural question: what are these psi gamma p and psi gamma p tilde? So are they related in some way? And the answer is yes, that psi gamma p and psi gamma p tilde they actually represent. So this word again. So if I look at the different phi gamma phi p and phi p tilde. Okay, let me suppress this factor of 2 pi. Kind of thinking. So that would be e to the minus y. Let me even take a different combination. Phi p tilde minus phi p. So that will be q plus e to the y minus q minus e to the minus y. But this thing is nothing but mirror superpotential kind of derivative, y derivative of mirror superpotential. So therefore these things, phi p and phi p tilde, so they represent the same class in Jacobi ring associated to mirror superpotential. So their difference is proportional to gradient ideal. So it is 1 times this derivative of WP. So there is a kind of an alternative way of representing this Jacobi ring. So we can represent Jacobi ring, which is this quotient of functions, homomorphic functions on C to the n, or equivalently functions of y, quotient by gradient ideal. So we can represent it as a cohomology of this operator QW, that is our QW, acting on some auxiliary vector space, let me call it U, auxiliary vector space U, and this vector space U, they are functions on kind of functions of y and functions of psi phi. So I can, let me write it in T. So let us introduce kind of an auxiliary space which is functions of y and psi phi. And on this space we have this differential operator that kind of differentiates with respect to psi phi and multiplies by dw over dy. So this QW is kind of Koszul-like differential for people familiar with that notion. But for people who don't familiar, so that is just some formal differential, And there is kind of a theorem, or I'm not sure maybe theorem, let's call it proposition. So proposition that if I compute cohomologies of this QW, I will just get a Jacobi. And then the proof is rather straightforward. Sorry, here I need H naught. So zero cohomology means it's cohomology on zero chains. So zero chains. So zero chains, they essentially so they are just functions. So we kind of so this differential cube it kind of changes a number of psi phi. So that's why we can count degree in psi phi as a grading. So zero grading means no psi phi. So these things are just functions on S1 to the power n. So that's our zero chain. So what about kind of zero cycles? So that is our zero chains. So zero cycles on this complex. So that matches with all zero chains. Like all zero chains, they are closed with respect to this differential, because differential takes a derivative over psi phi. So zero chains, they are zero cycles. So what about zero boundaries? So for a zero boundary, we need to look at the image of this differential acting on one chains. So one chains, they have this structure, so kind of C1 of U is essentially some, I don't know, Fk psi k phi. So it's just some function of y multiplied by psi. And then Q, what Q does, it kind of removes this psi and contracts this function with partial derivatives of y. So these things, they are holomorphic functions. They are functions of y of the following form. That is Fk multiplied by partial derivative of w with respect to yk. And we can immediately notice that this thing is nothing but an element of gradient ideal. The element from a gradient ideal is some function multiplied by generator. And therefore, zero's cohomology is a quotient of zero cycles, which are all functions of y molded by zero boundaries, which are elements of gradient ideal. And therefore H naught is Jacobi ring. These functions of y molded by
this function fk. Do we specify its range? I mean,
it's just periodic function of y, like any periodic function.
Any function.
Yes. Smooth function of periodic variable y. Yeah. So therefore we have this nice identification that we can realize Jacobi ring as a cohomology of some differential QW. And this very same differential QW, it emerges as kind of part emerges as this deformation of the family of HTQMs. Okay, let me write this example. And then now, kind of given this knowledge that Jacobi ring, we can realize the cohomology of some differential. So let us recall from last time. So let us recall that these mirror states, by construction, they were QX closed. And furthermore, they were G minus XZ. And I think two lectures ago, we kind of proved a theorem that if you have kind of correlation function of some states psi 1 to psi n in just abstract HCQN, which were both kind of Q and G minus closed. So then, as long as we change a state, that if we change one of the states by Q exact of G minus closed kappa, so let me just write it like this. So Q of kappa and kappa is also G minus closed. This thing is 0. So as long as we change something by Q exact of G minus closed, the correlation function doesn't change. And what we had, we kind of expressed this tropical Gromov-Witten invariance as correlation functions in some B model. But correlation functions in B model, like modular this small subtlety, they are kind of defined on QX cohomology. So essentially, correlation functions in the model defined by HCQN are defined on cohomologies of QX. So therefore, let us kind of compute this cohomology of QX. So QX itself is the sum of two differentials. So therefore, we can use spectral sequence to compute cohomologies of QX. Spectral sequence. Okay, so how we perform spectral sequence? So let us start with this kind of cohomologies of the first differential. So first differential is the Ram differential. So this radial de Ram differential, and cohomologies for radial de Ram differential is rather easy because our radial de Ram differential acts on kind of functions on a real plane. And on real plane, the only cohomologies are zero cohomologies. So it is essentially H0 with dr, and it's nothing but kind of constants in kind of R and psi R. And that is precisely our space U. So our space U was just kind of functions of y and psi phi. Kind of functions of psi phi and y variables. So cohomologies of the Ram operator on a plane kind of eliminates all psi R and R dependence. So we identify them, and then on kind of page 2 of a spectral sequence, what we need to do, we need to compute cohomologies of the second differential QW on cohomologies of the first differential, which means computing cohomologies of QW on this very same space U. And we already computed the zeroth cohomology of QW. So I think there is kind of general argument that all cohomologies of QW are in gradient 0. So that is not explaining this, but there is this fact. So therefore here, what we will get H naught of QW in U, which is Jacobi ring itself. So therefore, space of kind of B model mirror states. So for each kind of differential form gamma that represents cohomology class. So we constructed a mirror state. We constructed first a state psi gamma in A model, and then we dressed it to construct psi gamma x, which is a mirror state, which is kind of closed under QX. And the amplitude for this correlation function of these states is insensitive for shifting the state by qx of something. So therefore, essentially the kind of arguments for this amplitude or this correlation function, it depends on cohomology classes of this psi gamma x. And by observing that qx is the sum of two differentials by performing spectral sequence computation for cohomology, we arrive into very interesting statement that there is a kind of natural intensification from h star of x, where our observables live in tropical Gromov-Witten theory, to a Jacobi ring, where observables live in kind of Landau-Ginzburg Saito model. So that is our kind of tropical version of this equivalence relation. So here we just use kind of HTQM, some resummation of amplitudes, mirror states, spectral sequence to get this very old, well-known result that quantum cohomology of a toric variety X is Jacobi ring for its mirror superpotential. So here we already arrived at it in HTQM.
Maybe I need some time to formulate my question.
Okay. Okay. So let me still have half an hour to the end of my course. So I want. So far we achieved kind of two goals.
Sorry.
Yeah. Okay.
So in the radius part, this dr part, I mean the space is not the total Euclidean space, right? It's the polytopes.
But polytope is kind of Euclidean space compactified at infinity. So and yeah, I agree that there is this subtlety, but the fact that compactified at infinity kind of implies that cohomologies are trivial. So we kind of have actually a kind of more careful proof of this statement using certain pairing that is defined on both forms on Rn and forms on Rn with certain asymptotics. So this one is not kind of our main proof. So that is kind of short version of almost proof, but you are correct that there is the subtlety on kind of asymptotics of differential form.
Yeah, it's like if you compactify like one-dimensional Euclidean spaces, it will be like something like closed interval. So the Dron form of the homology of closed interval will be different from an open interval.
But they still will be concentrated in H naught. So for closed interval, it still would be maybe not one copy of H naught, but kind of maybe like two copies of H naught. So yes, it changes cohomology, but kind of not that drastic. So but I agree that was kind of not very strict argument. That was kind of motivational part, but unfortunately. Kind of this argument about pairing part, it requires like more than half an hour to explain. So yes, there is kind of better proof. Using pairing. But okay. Fortunately outside the scope. Okay, so far we kind of at least explained how we get superpotential here and how we get these states phi gamma, how we get them from kind of cohomology classes on X. That you start with the state gamma with the differential form gamma. with kind of gamma, which is differential form that's representative of a cohomology class, you construct a state psi gamma in A-type HTQM. You dress it to kind of mirror state psi gamma x, and then kind of take a representative in QX cohomology that is independent on kind of, that only depends on y. And that is possible because we expect that this cohomology class is identified with Jacobi ring. So we will get some element in Jacobi. Okay, so that basically tells us how to kind of map the data, but it doesn't explain why do we have inequality. So that explains it kind of how to verify inequality if you want to verify it. But the theorem is a stronger statement that not only we can formulate an equality that we can verify, but this equality will hold for this data. And for this kind of last step, so the idea of the proof for last step is the following. So remember that we rewrote tropical Gromov-Hit invariant using theorems 1 and 2. So 1 plus 2. So we rewrote it. Okay, so summit over beta. So that was correlation function of this psi gamma x, 1 psi x, psi gamma x in deformed B-type HTQM. So that's kind of where the theorems 1 and 2 led us. So then we noticed that due to these states psi gamma being Qx closed and G minus closed, so as long as we shift them by Qx exact of G minus closed, so then this correlation function is unchanged. So therefore we can do the following thing. So let us take psi gamma xn and kind of let us turn it into phi gamma n plus Qx of something. And in a case, in this example, for kind of delta function at a point observable for a P1, you can actually verify that this something, that this chi satisfies the additional property that G minus chi is 0. So if for this phi gamma, that is kind of a good section applied to class. But in our case, we have a very concrete representative, which is e to the plus y or e to the minus y. So that can be just verified. Okay, so having this property and having this theorem that we proved a few lectures ago, so we can rewrite the very same correlation function in the following form. So that continues. So we keep these observables gamma n minus 1 as they are, and here we insert the homomorphic function that is a different representative from the same QX.
Here, phi gamma n means the first term in the very long perturbation terms. I mean, there will be phi gamma plus k g minus phi gamma.
In a simple case of CP1, yes. In more general case, that is kind of more complicated. So that's kind of where pairing is important. So technically, using this pairing argument, phi gamma is the following thing. So we construct psi gamma x, and then essentially this pairing tells us that we can restrict to 0 psi, and we restrict to r equal to 0. So therefore, it's not just constant part, it is kind of constant part evaluated at a special value of r. Because constant part in general will depend on r. So, and to get function of y only, we need to evaluate it at a special value of r. So here, kind of, okay, at some fixed value of r. So here we choose 0 for the pairing that we introduced, but we can modify our pairing to kind of localized at some arbitrary fixed value of r. So that is kind of a technical formula for how we technically get phi gamma from psi gamma x. And then there is a separate theorem using this pairing to show that they actually belong to the same cohomology class, that their difference is qx of chi for g minus closed chi.
Actually, is this construction the same as your cytogood section? You said it's unpermanent.
No, cytogood section is a map from Jacobi ring classes to holomorphic functions. So and here we are still doing something in HTQM. So that's why it is not cyto construction in any form. Okay, so on the first step, we kind of replace one of the mirror states by a holomorphic function using this procedure. And because of the theorem, the answer doesn't change. So now we use another theorem that we also proved a few lectures ago, which was a kind of a relation between n+1 point correlation function and n point correlation function. So remember, here we call it psi 0. So we never specified which state we use. We just state that as long as psi 0 is qx and g minus closed, which automatically true for this thing, then we can reinterpret this correlation function as a derivative with respect to epsilon at epsilon equal to 0 in L-deformed theory. So we deform with psi gamma, we deform them with this phi gamma n state. And we also deform our differential in some okay, sorry. We call them upper script epsilon. So we deform our differential by epsilon. And so that was also some theorem that we proven a few lectures ago. So now let us look at these states. Okay, so first let us look at our differential. So the formation of differential was done in the following way. So it was original differential. Sorry, not PW, QX. Because QW is differential in different spaces. QX. And here what we have epsilon and once again G minus commutator with a multiplication on a state psi naught. So that's what we got. But now, if our state psi naught is not kind of an arbitrary qx g minus closed state, but actually a holomorphic function, or actually a function of y variables only, so then what we would get the following things. X deformed by epsilon, here would be derivative of this function with respect to yk e over d psi phi k. So we just explicitly computed this deformation for our special choice of state. And that was the reason why we wanted to turn this state into function of y only to get this very nice expression for deformation. And now, if we recall that qx itself was a radial deram plus a similar thing for w, so we can rewrite this object in a very nice form that is QW epsilon. So we can kind of treat this deformation of Qx differential as a deformation of W, and W epsilon is nothing but W plus epsilon phi gamma n. So after this kind of change of the representative and applying this theorem, we observed that Qx epsilon is nothing but kind of Q computed not for a mirror superpotential Wx, but Q computed for deformation of a mirror superpotential by epsilon phi n, by epsilon phi gamma n. And that start looking very much like a recursive formula that we have in Landau-Ginzburg-Saito theory. Because in Landau-Ginzburg-Saito theory, we precisely deform our superpotential by epsilon n's holomorphic function. So here we got that part. So what about this state psi gamma x? So here we got this nice formula that this thing is Q Wx deformed by epsilon. So in the case of psi, so now we want to compute this. So psi gamma x epsilon, and that is by construction psi gamma x plus kg minus, and here we need to multiply this psi gamma n by psi gamma x. And now once again, let us recall that this thing was psi gamma plus kg minus wx multiplied by psi gamma, plus kind of higher order terms, higher order dressing. And then we have kg minus phi gamma n, and here we once again substitute this thing. So psi gamma plus psi gamma plus kg minus wx psi gamma plus dot dot dot. And it's not kind of hard to see that we can combine this expression into following formulas: psi gamma plus kg minus wx epsilon psi gamma plus kind of continuing dressing by wx epsilon. And that would be different from original expression by terms quadratic in epsilon, because in double dressing by wx epsilon we would have something like epsilon square and double dressing by phi gamma. That is absent in original expression. So that kind of basically tells us that not only phi gamma deforms superpotential, but it deforms kind of dressing, or it deforms these mirror states in kind of the same, so deforms in exactly the same way as deforming superpotential. That kind of, we can schematically write that psi gamma x is kind of psi gamma dressed by this wx sort of insertion. And then psi gamma x epsilon is nothing but psi gamma wx epsilon in kind of leading order in epsilon, like up to order epsilon square correction. So therefore we got a kind of an interesting statement that correlation functions for a states dressed, for correlation function in HTQM deformed by wx for the states dressed by wx endpoint function equal to epsilon derivative with respect to epsilon of n minus 1 point function in HTQM with deformed superpotential and a mirror state constructed from deformed superpotential. And we can iterate this procedure and then in this new theory we can take this psi gamma n minus 1 deformed and turn it into holomorphic function for wx deformed. And continue this procedure all the way till we, like naively you would say, we can just iterate this procedure and replace all psi's by phi. However, there is a subtlety, and subtlety is that if we formally compute, so let us recall the 3-point correlation function for psi's was something very easy. It was mu30 on this psi's. So that was mu30, psi1, psi2, psi3. And this thing was what essentially we multiply this psi's and just integrate over something. So in these notations, we will integrate over kind of ptx cross s1 to the power n. So the problem is that the moment we replace all psi's by phi's, this integral becomes ill-defined. Because okay, integral over s1 to the n is well defined, but the integral over radial variables is not defined because we're trying to integrate constant over infinite range in radial variables. So this thing is ill-defined, and therefore we need to kind of regularize it in some way. And that's kind of where pairing that I haven't introduced will help us again. That kind of we can regularize this integral by adding e to the q of something. So formally, if integral exists, adding this factor e to the q of something would not change the integral, because the integral of q of something is just 0. However, if there is some issues with the integral, then these terms e to the q of something can regularize the integral and kind of make sense for it. And it turns out that this expression, regularized expression for a 3-point function, so if we now compute it for 3 holomorphic functions, for 3 functions of y only, for phi1, phi2, and phi3, so this kind of integral ptx cross s1 to the power n of 3 functions, phi1, phi2, phi3, e to the sum qx of some lambda, that this integral is equal to precisely a residue formula that we use as kind of base of our recursion in Landau-Ginzburg Saito. So and that is kind of strategy of our proof that first we kind of treated as separate case 3-point functions, that we look carefully at a 3-point function, then kind of regularize it by e to the q of something, such that with this regularization we can replace psi's by phi's. So with integral being still well defined. So for psi's this regularization does nothing. But for phi's this regularization makes integral well defined. So therefore we can play this trick with replacing psi's by special representative phi, which is function of y only, and then kind of computing this integral will kind of localize us to some residue formula, and then because of this theorem that allows us to remove one state and use it to deform remaining states and HGQN. So we observe that if we first replace this state by just function of y, so then the deformations of HTQM would be equivalent to just deforming superpotential in the same way as we do in Landau-Ginzburg Saito model. So So this statement became essentially a kind of Landau-Ginzburg-Saito recursion. And for a 3-point function, we showed that the correlation function equals to Landau-Ginzburg-Saito formula. And then for, say, n-point function, we just prove it by induction. That kind of assuming that it holds for n-1 point function, then we do this procedure and reduce n-point function equality to some linear combination of n-1 point functions equality. So that kind of explains how we get an equality between amplitudes and correlation functions in Landau-Ginzburg-Saito. So the last bit that remained in the theorem 3 is the kind of good section part, because so far we kind of haven't seen good section. So here we saw that there is this formal recursion that holds, and 3-point function work. So the last bit that we need to do, we need to check the following thing. That you see here, we have our state, our kind of deformed state after we deformed it with phi once, with phi gamma n once. And then if we want to, then we can turn this state into some kind of holomorphic function phi gamma in kind of cohomologies of q wx epsilon. And once again, so this state would have some epsilon expansion. So it will be like phi gamma. So that would be the state in QWX cohomology if we just turn psi gamma into phi gamma. Plus epsilon times some constant term, times some some contact term. So that's what Landau-Ginzburg-Saito model tells us, that the deformation of these states as we perform Landau-Ginzburg-Saito recursion is done by a contact term between phi gamma and phi gamma n. So therefore, in order to compute contact term, we need to kind of perform this procedure, like computation of phi gamma, for this state. And that's kind of the last bit of our construction is to kind of verify that if I apply this procedure for getting holomorphic function from HTQM state, and if I apply this procedure before the deforming HTQM and after the deforming HTQM, that the difference would be a kind of Landau-Ginzburg-Saito contact term that is defined in very particular. So and that is kind of the last bit of our construction. That is quite technical. So there is kind of no good shortcut. So we really kind of.
Excuse me, what is this green stuff?
So green stuff is what we expect from Landau-Ginzburg-Saito model.
That it's phi gamma dot phi.
Okay, let me write it into the right. That's an important formula. So phi gamma epsilon phi gamma plus epsilon phi gamma n. So if Landau-Ginzburg-Saito recursion, we perform recursion in phi gamma n, so then the change in other states would be by shifting by contact term between phi gamma and phi gamma n.
Previously, the other states are psi gamma.
Yes. So we have psi gamma epsilon. So we have the state. So let me compare this. So that is Landau-Ginzburg-Saito, and HTQM we have psi gamma x deformed by epsilon, and the formula is psi gamma x plus kg minus of psi gamma x with phi gamma n. So that was the deformation of state in a recursion theorem for HQ. So now what we can do, we can apply this procedure, apply this localization to turn this into phi gamma in deformed theory, phi gamma x. So this would be phi gamma undeformed. And that would be, okay, some localization of, so we first need to compute this thing and then kind of localize it to psi equals 0. And then the last theorem, that this bit kg minus of psi gamma x with phi gamma n matches with this bit, which is kind of standard contact term in Landau-Ginzburg-Saito model. So that kind of the last bit to prove this main theory. That not only we have recursion, but the kind of deformation of states on each stage of the recursion is given by a kind of contact term style formula for a certain good section. For a certain good section. And we kind of call this good section because it comes from a tropical mirror construction. We call it tropical good section. So this expression equal to this expression for a tropical good section. And we can describe this tropical good section in kind of in the following way. So let me just.
You mean this CW is determined? Yes.
Yes, determined from this relation. That is what we have from massaging our tropical Gromov invariant. So then we interpret this thing as a contact term with some good section. And kind of it turns out that the tropical good section, okay, the image of a tropical good section is given by a following construction. So it is linear span of nothing but kind of phi gammas, phi gamma alpha and gamma alpha kind of runs over cohomology classes of X. So for each cohomology class, we take a kind of representative, which is U1 to the n invariant. We construct a mirror state psi gamma. Sorry, we construct a model state psi gamma. We dress it to a mirror state psi gamma x, and then we perform this localization procedure to turn psi gamma x state into phi gamma into function of y. And then we say that we perform this for representative of each class, each cohomology class, take a linear span, and that would be the image of good section. The image of tropical good section. So in some simple cases like CP1, where kind of site of good section is known, so our tropical good section for sure matches with a known result. So unfortunately, for mirror superpotentials, even for projective spaces, I think literature doesn't know the answer for site of good section, and therefore our tropical results, so we don't have anything to compare it. But kind of our whole construction and our main theorem basically tells us that even if Kürji site of good section is non-unique in a mirror Landau-Ginzburg-Saito theory, there is at least one special choice of this non-unique good section, tropical good section, that would give us correct Gromov-Witten invariance from Landau-Ginzburg-Saito theory. Yeah, and I think now I'm out of time. My course. Yeah. So, but at least maybe sketchy, but we managed to get at least sketchy proof of a final theorem. So. Okay, yeah, and so formally next week would be final exam, but I will notify you and Louis. I'm not sure whether we want to have it during lecture time or some other time. I think the institute allows us to be a bit more flexible on that one. So as long as we kind of do a final exam before some fixed time, I think it would be okay. So let's kind of talk to Louis to see what his preference. Okay, so and also for Louis, I kind of graded first three homework. So I will upload the grades and solutions like after the lecture today, and I will grade homework fourth and fifth, which Louis also submitted sometime later this week, hopefully in the next couple of days, such that before the final exam, Louis would have like all homework graded and all homework solutions. Because I think in homework 1 for WDVV, I think he got some mistakes. So he did very well on homework 2 and 3, like almost no mistakes. But for WDVV, he got like confused in some summation. So okay,
thank you. And I have a question. Here, this previously you give us a motivation that what is the localization? It's like you take the R0 in the delta form to plus or minus infinity. But here you select another construction, right? It's like you take C to be 0 and R to be 0, then you select such thing to be your representative.
Yeah, but as I say, like there are like so these phi's, they are defined modular kind of this QW shifts. So that's why these phi's they are not unique.
Yeah.
So these phi's always guaranteed to be in an image of a good section, but they can belong to.
Yeah, because in the previous example, in the point class, in the CP1 case, you take R0 to plus or minus infinity, get some representation of that class. And first, in that case, in the CP1 example, can you take R0 to be some intermediate value?
Yeah, you can set say R0 to 0 and like if you simultaneously take psi's to 0, so then instead of single exponent, you will have like sorry not R0, you take R to 0. So therefore what you would get some linear combination of two exponents parameterized by R0. So what you would get like psi gamma point 21 and localized. So that would be like theta function of R0 e to the y plus theta function of minus R0 e to the minus y. So therefore you kind of now have a family of kind of representatives. So if you choose your R0 positive, then it is e to the y. And for R0 negative, it is e to the minus y.
And premise, do you take this C to be 0? Or you just take
R0?
so
that is part here, psi to be 0.
But I remember you also take R0 to be plus or minus, just to be very positive and very negative.
But that was kind of different construction. So as you see here, so we are still kind of landing in some elements of Jacobi ring. But
In that construction, the representative differ by some element in Jacobian ring, just like what you showed in minus plus infinite case. And here, you mean
yeah, but here with this procedure, we would get like depending on R0, we would get different elements of Jacobi ring. But with this procedure, we would get an element from a good section. So we would get not just class in Jacobi ring, but special representative of a class. And in this case, it's kind of either e to the plus y or e to the minus y. So they are both kind of equally good special representative.
I have a simple question here. Qx chi is an element in Jacobi ring.
No, Qx chi is a state in HTQM.
Yes, but in the yes, I asked it because like in the mirror, in the Landauer's recital case, you also select some representative according to the good section. And here in the deformed A HTQM case, you also select some representative.
Yeah, and as I say,
they decide each other, I guess.
So they are both kind of representative from a good section, because as I say, so there is this kind of whole story about pairing, and kind of both of them satisfy this additional Saites condition that higher pairings on, so there is this condition that higher pairings on images of a good section vanish, and what we check that for this representative, the higher pairings understood written in the language of HTQM also vanish for pair of states of this form. So as I said, like some things are kind of not immediately obvious from what I explained, because there is this kind of a whole section about pairing and manipulation with pairing that I skipped. So
okay, naively, can we compare the second line? Per CX is like deformation of this phi gamma, and this deformation phi gamma epsilon equals to phi gamma plus some.
because they are in different spaces, so you can't compare. So one is deformation of like holomorphic function, and another is deformation of HTQM state. So HTQM states is kind of it's much bigger space.
Somehow you can use HTM to project to the Jacobi ring, like in this.
Yes, and that is this part of this pairing business. That under projection you don't change the value of a pairing and
also, can I say this projection of Qx chi is the term here CW?
No, as I say, they are in different spaces. They are not the same. So this term is what I wrote here. It's kg minus psi gamma x phi gamma n computed in HTQM and then localized to psi equal to 0, r equal to 0. So that's that kind of the only construction that gives you kind of Landau-Ginzburg form. And unfortunately, you can't mix these two states because yes, holomorphic functions, they are formally states in HTQM, but they usually lead, if you just try to evaluate amplitudes on these states, then you will typically lead to some kind of undefined answers like 0 times infinity or something. So therefore you need to be careful, because to make various equalities, you need to make sure that amplitudes for the states that you substitute, that all these amplitudes make sense.
Okay, so this localization process will kill the Qx chi part. You do like,
yeah, so that's why we do it only one by one. So that's why we don't apply it to all states simultaneously, because even I think if we apply it to two states simultaneously. There is a chance, like there is some situations, like some arrangement of other states and kind of toric variety, such that this expression would be ill-defined in a sense that it will be something like 0 times infinity. So, however, if you kind of turn only one HTQM state into holomorphic function, then we showed that in this situation all amplitudes are still well defined. So therefore we can write down an equality between one well-defined correlation function or linear combination and another well-defined correlation function with a different representative for cohomology class of one of the states. So that's why in this situation you need to be careful, because the formulas might exist and might make sense on a level of observables, that as observables the things are related in some simple way. But unfortunately, the moment you try to plug in these observables into some realistic correlation functions, you run into something ill-defined. And that kind of makes all relation for observables useless, because we eventually not interested in localizing observables, but we are interested in proving this kind of tropical mirror relation, where one correlation function for one kind of observable is equal to a different kind of correlation function for a different kind of observable. So yes, it is true that if we work on a level of observables, we can take a lot of shortcuts, and that's kind of what people in the literature do. So they take the shortcuts, they arrive into some ill-defined correlation functions, and they just leave it there, saying, oh, we can probably regularize this correlation function some way that it matches. And that is not what we are doing, and we spent like a lot of time and 80 pages for just part 3 to make sure that this relation not only on the level of observables, but on a level of well-defined, on a level of equality between two well-defined correlation functions for these observables. And therefore here in many steps we need to be extra careful, because not only we need to kind of carefully relate observables, but we need to make sure at every step that we kind of still keep our correlation functions well defined. So that is some kind of take-home lesson, that some formulas appear much simpler than they are in fact. So
yes, this correspondence from psi gamma to phi gamma. There is an intermediate observable psi x, which seems to be a homologic perturbation of psi. It's like psi plus psi kg and kg psi. Yes,
yes, it is homological perturbation, but as I say, it's kind of not helpful, because we are not talking on a level of states or even deformation of differential, but we are talking about and not even pairing, because kind of pairing between states is usually situation when you have two files, and we are talking about some more complicated objects, which something like a Massier operations for these states and differential, and I don't know like what happens to all this homological perturbation theory on a level of Massier operations or some more complicated objects like that. So that's why, yes, it is homological perturbation theory, but unfortunately it doesn't help us to prove the tropical mirror relation.
But your construction of this phi gamma seems to be some embedding, maybe some natural.
Yes, it is embedding, because not embedding, it's actually projection. Phi gamma is a projection of psi gamma x onto cohomology. So we talk that cohomology of Qx is elements of Jacobi ring. So and this localization formula is essentially projection from states in HTQM to elements in Jacobi ring. So yes, it is a projection, and yes, you have canonical embedding by treating function of y as an HTQM state. But this simplicity is kind of deceiving, because kind of if you kind of overuse these projections in embedding, the amplitudes will typically become ill-defined.
Does this, like something like homological perturbation, has some explanation, like in enumeration or something? Because you have
but everything here is enumeration. We are talking about natural numerative problem. Like every single expression here can be traced down all the way to tropical Gromov-Fitz invariant.
But you modify the state C to be
X. But eventually it is constructed as a linear combination of some enumerative invariants. So all these modifications, like you can re-expand everything and write down every single correlation function in terms of A model correlation functions, and in A model all correlation function equal to Gromov-Fitz invariant. And that is kind of main advantage that makes sense of all this activity, that at every single step, if kind of expression, if the correlation function is well defined, so if there is no 0 times infinity issue, then we can kind of re-expand everything back in terms of A model expressions, which itself well defined because they are equal to tropical Gromov-Fitz invariants. So therefore here there is kind of no question about enumerative meaning, because
I mean there may be some elementary explanation of this.
I'm not sure. Like if you read papers about usual mirror, like comparing to what people do in there, our explanation is like super elementary. And I kind of doubt that you can go even more elementary than that. So usual mirror symmetry is kind of very, very complicated construction, especially in this context of mirror photoric varieties. So and usually it's kind of, in most cases, it's just verification of a mirror relation rather than proof by explicit derivation. So that's why I kind of highly doubt that you can go more elementary, because in our case simplifications was due to this huge power of tropicalization. And going more elementary means that there should be some input at the level of tropicalization. And at least I don't know about this input, and I kind of highly doubt, because in our case I'm not sure that. So so there is like a separate activity which is trying to kind of rewrite these correlation functions in Landau-Ginzburg-Saito model as a correlation function in a simpler version of HTQM, not B model HTQM, but HTQM at a smaller space. So here in this localization we saw that the space for HTQM states has like way more variables. It has psi r, psi phi, and r variables. So there was a kind of conjecture by Andrei Losik that maybe we can reformulate Landau-Ginzburg-Saito model as HTQM on a space of states which is U, which is with functions on just y and psi phi. So maybe if you just add y and psi phi, so then, for example, we have a natural differential Q double reacting on this space. And you can, and actually G minus also acts on this space. So there was a natural question whether we can run HTQM on this space, some kind of HTQM on this space, whose correlation functions would match Landau-Ginzburg-Saito model. And as far as we try it in some cases, very much likely the answer is no. That there is no HTQM on this space that reproduces kind of Landau-Ginzburg side correlation function. So that is very strong argument that kind of next space, when we just add like another copy of two variables like R and psi R, so that would land us into our B-type HTQM. That might be a kind of a minimal HTQM model that reproduces kind of correlation functions in Landau-Ginzburg cytomorph. So and that's why that is very strong evidence that there is kind of no smaller thing that can capture things here. But that is kind of an interesting question, and as I say, that's where I'm kind of have different opinions than Andrei Losev. So he still believes that maybe we can kind of do something else here, find some nicer homotopy for QW that is not HQM type homotopy that would kind of give us this Landau-Ginzburg side correlation functions as the sum of certain amplitudes. But so far, I think in all kind of examples we failed in some simple. Yeah. So that is my argument about kind of having some simpler interpretation. It seems that HTQM is as simple as it can get.
Yeah, sorry, one more question here. And you basically have two states, gamma 1 to gamma n, and then gamma b, some BA to B.
Okay.
Yeah. Does this state correspond to some constant loop, or?
I don't know. Like as I say, I don't know how this HTQM is related to HTQM for kind of more serial loops. I don't know.
I see. Yep.
There might be some localization from one HTQM to another HTQM, but I don't know.
It seems that the gamma 1 0 type is like a constant loop insertion, and the 1 BA is something like
but one thing
periodic
it seems like, and other thing is to prove theorems about it. Like so that I want to kind of stress this thing that what I talked in my course and what we published in our papers was a strict, in mathematical sense, proof of a tropical mirror symmetry in a setting of a toric variety, like proof using standard methods of mathematics. So no path integral, no kind of quantum mechanics via path integral. So everything was like some kind of simple functional analysis or something. So and I want to stress out that kind of the level of kind of rigorousness that I want to keep in this activity. So that's why even going to a loop space that makes things kind of less rigorous, because for a more serial on the loop space there are like a lot of issues like absence of Morse synthesis and stuff. So and it requires some kind of very careful justification. But here we are doing like ordinary quantum mechanics of some particles. Yes, our vector spaces are infinite dimensional, but it's kind of infinite dimensional space of states for some finite dimensional motion, while quantum mechanics on the loop space is like infinite dimensional space of states for a motion in infinite dimensional space. So that kind of a way more complicated infinity. And And I kind of think that if we want to relate one to another, then we should kind of keep the same level of rigor. That first we need to kind of carefully define and understand kind of Morse theory on the loop space, see where Gromov-Fit invariants are there, and then maybe take a tropical limit and see whether the thing would simplify in a tropical limit. And by simplify, I mean not on the level of states in HQM, but on the level of actual amplitudes that equal to Gromov-Fit invariant. So, which is, as we saw in working with this kind of HQMs, it makes a big difference. That getting this formula for a mirror state, so it took us like a few days, and getting a complete proof for amplitudes took us like maybe a year and a half. So because there are a lot of subtleties. So that's why, yes, the things may look similar, but I think we are working on a level of proofs of the theorems, and I would like to see like some carefully formulated statements and their proofs. So before I will kind of commit myself to saying that things are the same or not the same. So maybe we will reach it at some point, but right now I think it's kind of still too early. So we still need to finish kind of getting Gromov-Fit invariants and WDV equation from Morse theory in the loop space, and then we can try something like a tropicalization to see whether we can simplify things on that side. Okay, so I need to go.
Thank you very much.